Alrighty, you're over the first hump of O-Chem 2. It's almost smooth sailing from here on out. Trust me. So now we're diving into chapter 17, which means we're back to reactions and reagents. No, I don't want you to think of it that way. I want you to think of it as back to electrophiles and nucleophiles, because this may come across as a fairly overwhelming chapter, but it's just review. So believe me, you can do it. We have two new nucleophiles, and actually they're not new. We've seen them briefly previously. The big new thing is the electrophile. So now we're introducing a polar pi bond. Pi bonds we've been looking at so far, pretty much darn nonpolar, just plain old alkenes or alkynes. But due to the bond dipole between the carbon and the oxygen, we've got a great electrophile. And this electrophile encompasses a whole bunch of functional groups. It encompasses aldehydes and ketones, or esters, acid chlorides, amides, and acetic not acetic, just plain old anhydrides. I mean, there's a lot of electrophiles, but they all have that crazy electrophilic polar bond in common. So mechanistically, the good news is you're pretty much going to see the same thing over and over and over again. If my nucleophile is that nifty H-, it attacks, as you might expect, at the electrophilic carbonyl carbon, and showing you that we're making a new carbon-hydrogen bond. So here's the deal. That part should be pretty straightforward. H-, nucleophile, carbonyl electrophile, pops up the pi electrons onto the oxygen. Good and well. But what happens next depends a lot on the nature of the Y group. So if Y is a lousy leaving group, for example, a hydrogen or an alkyl group or just any carbon, then it's going to stick to that carbon. It's not going to come off. Everything's going to stay intact, and the only thing that can happen next is that O- gets protonated, typically, in a workup. And so you've made this new carbon-hydrogen bond, and you just protonate to give an alcohol from your CO double bond. But what if Y is a good leaving group? Okay? In that case, your hydrogen in this example has added and nothing has come off. But in this example, if Y can leave because it's a decent leaving group, well, that pair of pi electrons is going to slap back down and kick out a good leaving group. That regenerates the CO double bond, but as you can see, there's been a substitution. In this case, the H- I added has substituted in and kicked out that Y group. So there's two main mechanisms for like the next 4 chapters. The addition reaction shown up above, and this reaction, which is substitution. This chapter focuses solely on addition, and then chapters 21 and 22 look at the substitution reactions. The beauty of it all is that as we go from polar pi bond to polar pi bond to polar pi bond. These are all polar pi bonds. Delta plus, delta plus, delta plus. You get the picture. Doesn't matter how big the molecule is. This is all chapter 1 stuff. Bond dipoles. And the beauty of it all is that they all react with the same exact mechanism. So don't be overwhelmed. Now, as soon as I say that, I tell you there's a twist, but it's a twist that you already know about. When we looked at IR, we looked at the stretching frequency for a regular old ketone and saw that the stretching frequency for the CO double bond is about 1720. But if we had a conjugated CO double bond, the wave number was shift down about 20 wave numbers. And the reason why is because of all that single bond character, because of the resonance contributor shown here. So the fact that you can draw that resonance contributor gives this carbon-carbon bond some single bond character, as it does for the carbon-oxygen bond. So it's localized here, but in the conjugated carbonyl there's a significant weakening of the CO bond. Okay, so that's something we've already seen. Another thing we've already seen is butadiene. How butadiene acts kind of odd because of that multiple center molecular orbital that's spread throughout the entire 4-carbon chain. So when we add chlorine to this conjugated diene, we saw that you could have 1,2 or 1,4 addition. Why? Well, because of the multiple center molecular orbitals, and because we could draw resonance contributors that illustrated how the double bond could shift in the carbocation intermediate. So now when we look at conjugation in the context of conjugated carbonyls, well, we're going to use the same principles. We can see that there is just the plain old resonance contributor shown by this pink arrow that illustrates why this is electrophilic in the first place. There's supposed to be a double bond there. But in addition, we can do a little shift-o there to put the positive charge here. So there's 2 major resonance contributors for a conjugated carbonyl, and that means there's 2 electrophilic carbon atoms. A nucleophile could attack here, or a nucleophile could attack here. If the nucleophile attacks at this carbon, that's called 1,2 addition. When we consider this 1 and 2 and 3 and 4, just as we did with our conjugated butadiene. If our nucleophile attacks at that carbon, and in this particular example, these examples that I'm showing you, the nucleophile I'm using is H-. Well, if the H- attacks here in a mechanism we'll get to, you get 1,4 addition. So we'll ultimately get to this a little bit later in chapter 17, but just keep reminding yourself, you've seen all this stuff before, just in a slightly different context. So it has obvious connotations in terms of figuring out what reagent you'll use to do 1,2 versus 1,4, but it's sort of sensible. Alright, the last major point I want to make in this introductory mini lecture is that aldehydes and ketones obviously react the same way. However, aldehydes are more reactive than ketones. How are you going to keep that straight? Why would that be? Well, hold on a second here. You've learned this reaction. You know that HCl adds to an alkene, and you know that it reacts with Markovnikov regiochemistry. Well, why? Well, you know why. It's because the proton adds to give the more stable secondary carbocation. Well, why is the secondary carbocation more stable? Because it has two carbons that are pushing electron density in towards the carbocation carbon to stabilize it. The primary carbocation only has one. So this is an example of an electronic effect where these alkyl groups are electron releasing, stabilizing the more substituted carbocation. Okay, so electronic effect is important. Okay, now what about this example? Why is it that under basic conditions we would see that the acetylide reacts specifically at the less substituted carbon to give you this product? Well, that was an example of sterics. Because there's no positive charge buildup from protonation on the oxygen, of course this nucleophile is going to take the path of least resistance. This carbon is more accessible. It's less sterically hindered. So we use sterics to explain this example, this outcome. We used electronics to explain this outcome. We used electronics to explain lots of radical chemistry in chapter 25. So we're kind of used to using sterics and electronics to explain things. So as usual, they're going to be used again here to explain the difference between the reactivity of aldehydes and ketones. Ketones have two alkyl groups pushing electron density into my electrophilic carbon. That makes this a weaker electronically, a weaker electrophile, because there's not as much of a delta positive there because of the electron releasing R groups. In addition, R is a bad thing to use here. Let's make it CH2CH3. CH2CH3 versus, say, an H. An H is about as tiny a little atom as you can get. It's just a darn 1s orbital. But CH2CH3, well, carbon's a lot bigger than hydrogen. It's got these two hydrogens and another methyl group attached to it. So sterically, it's also very much reduced in reactivity because the nucleophile is going to have a harder time getting through that electron cloud to get in there and attack that carbonyl carbon. So those are the big overview introductory points. You might want to review them from time to time because as we throw more and more reagents at you, you're going to think, oh my God, how am I ever going to keep this straight? But it's all based on the fundamentals that you learned in 2301. And to that, I will point out that we're even going further back. We're going all the way back to chapter 1 at the beginning of the next mini lecture to talk about oxidation states, which we briefly touched on but never really did anything with. And then we will dive in to reductions. So more fun to be had. See you in class.